Okay, hello everyone, and welcome to Emory Climate Talks. My name is Eri Saikawa, and I'm an associate professor of environmental sciences at Emory University. This webinar series is made possible by our anonymous donor that supports our trip to the UN climate change negotiations, and Emory Climate Talks is in partnership with the Department of Environmental Sciences and the Resilience and Sustainability Collaboratory at Emory University. For this talk, I would like to thank the Center for Faculty Development Excellence for co-sponsoring this one. Thank you, as usual, to Leah Thomas for doing everything behind the scenes. This webinar is being recorded, as you might have noticed, and we post most of our webinars on our YouTube channel. For recording purposes, we have muted your microphone, but if you have any questions during the talk, please feel free to use the chat function to type up the questions so that we can raise them during the Q&A session. Today, I'm so excited that we have Professor Asmeret Berhe, speak on soil biogeochemistry and also on making inclusive environment in academia. Black Lives Matter movement, and with the recent Asian hate crime incidents, I am delighted to have her provide important insights and to have a chance to discuss it together. I'm in the Association for Women Geoscientists, and I have actually entertained the idea of doing a webinar series inviting speakers. My idea was really to invite her and a couple of others. That webinar series did not really come into fruition, but I'm so glad today that we are able to have you speak with us. And this is only because Dr. Debjani Sihi also had the same idea to invite her. And unlike myself, she took action and invited her here. So I'm so extremely delightful for all that Dr. Debjani Sihi did. So thank you so much. Dr. Sihi is assistant professor in the Department of Environmental Sciences, and we are so excited to have her join us since last fall. For those of you that have not watched her brilliant talk that she gave at Emory Climate Talks herself, I would like to encourage all of you to check it out. That is actually the most watched webinar on our YouTube channel, more than the one with Naomi Klein. So we hope you watch Dr. Sihi's video and subscribe to the YouTube channel if you have not done so yet. We also have an exciting program that is coming up. So we hope you would also subscribe to our newsletter as well. Okay, so that is all the logistics I have. And I would like to invite Debjani to introduce our speaker. Thank you so much, Debjani, for making this happen.
Thank you so much, Dr. Saikawa. That was delighted to know. I'd like to invite Dr. Asmeret Berhe, and thank you so much, Dr. Berhe, for accepting my invitation. As you can see from the number of participants, we are so excited to have you. So Dr. Berhe is a soil biogeochemist. She is Falasco Chair in Earth Sciences, Life and Environmental Sciences Department, and Interim Associate Dean of Graduate Division at the University of California, Merced. So as you can imagine, Dr. Berhe worked at the intersection of soil, climate change, as well as political ecology. So all this really blends itself into a number of global issues. So Dr. Berhe, as you can already imagine now, is an advocate for women in science, as well as renowned for addressing issues of race and racism in natural sciences, mainly soil and earth sciences, as well as geosciences. She has won multiple prestigious awards. I will name only few because of the time today. So she earned Johannes Simpson Medal from American Geophysical Union in 2020. That is, the medal is being given to a mid-career scientist for doing outstanding contribution in the field of earth and space sciences. She also earned a Great Immigrants Award from Carnegie Corporation of New York in 2020. Randolph W. Bell and Cecily T. Bromley Award from Geological Society of America in 2019. And also she is the first cohort of the New Voices in Science, Engineering, and Medicine from National Academy of Sciences. If you haven't seen already, please watch out her TED Talk, which is now seen almost for close to 2 million times. And as you have hear from Dr. Saikoa, so if you watch out to my Emory climate talk, you will realize that my talk was greatly motivated by the work that Dr. Berhe do herself. So without further ado, I would like to welcome Dr. Berhe, and the virtual podium is all yours.
Thank you so much, Debjani, for that really generous introduction and for inviting me to join you. And thanks again, Ari and Leah, for making this possible. I'm delighted to join you all today and Emory and share with you how I think about soils, climate change, and inclusive diversity in our academic communities and its implication. So let's get started. Okay, so because you all don't know me, I figured I should start by introducing myself and the kind of work that we do in my lab at UC Merced, and then we'll get to the topic of soils and climate change. And I would like to spend the last third of the time that we have to talk about equity and inclusion in the academy. And I will try to make an argument for why this is important, even for the topics I'm discussing in section 2 of soils and climate change. Okay. So start with the lab. So we're a soil biogeochemistry lab, meaning a lot of the work that we do focuses on improving our fundamental understanding of how carbon, nitrogen, and phosphorus cycle in the earth system. These are critical essential elements in the soil plant atmosphere system. So their cycling has a lot to do with soil health, environmental health overall. In particular, we focus in my lab on responses of soil organic matter, so the organic component of soil, and how its abundance, persistence in the soil system, and overall dynamics is controlled by physical forcing. So what happens to soil organic matter and soil's ability to store carbon, nitrogen, or phosphorus when there is sudden physical change in the environment that occurs as a result of something like erosion that causes lateral redistribution of topsoil, or fire that combusts biomass, right, and cause a whole number of other environmental changes, as well as what happens during global change situations, including what the results of increasing atmospheric temperature, or what happens during situations when you have change in amount, timing, or abundance of distribution of precipitation. All of these are really critical because these are things that we're experiencing on the Earth system these days, and with more vigor and intensity, obviously. But there are also fundamental mechanisms that regulate these biogeochemical cycles. And so in our work, we try to spend time thinking about climate change, climate impacts, and what kind of role soil can play in climate change mitigation. And then we're allowed every once in a while to also use this perspective that we have and put it together with political ecology to understand dynamic human-soil interactions. For those of you who are not familiar with the term political ecology, it's a field study that uses political economic theory to explain and understand the relationships between human beings and the resources that we depend on. And in everything what we do, we try to employ principles of justice, equity, diversity, and inclusion in our lab. And this is not just in terms of who we welcome into our lab and who we're giving an opportunity to join us to do this research, but also to inform how we do the research that we're actually carrying out. So, broadly speaking, the motivations for our work, as you've seen at the fundamental level,
Did we lose her?
Yeah, I think we're having some issues.
Yeah, I don't hear her.
I know it happens all the time.
Sorry about that. I guess it's these days that So anyway, I was just saying the fundamental motivation is improving understanding of soil processes and how they occur, but then that more contemporary concerns that have to do with human soil relations, in particular in the context of how soil use, overuse, and abuse by human actions is now affecting not just the health of the soil system, but also has human security and national security considerations. Okay, so in the next few slides, I've listed a few topics that have become major topics of research that we do in our lab. And I've listed a few papers, in particular ones that are more review or synthesis type of papers that represent overall the body of work that we do at the bottom. But I'll just zoom through these just to give you an idea. So one of the longest standing topics we've been investigating in our lab is how erosion controls not just lateral redistribution of topsoil and associated soil organic matter, but also to address whether erosion as a process in the earth system represents a net sink or source with respect to atmospheric carbon dioxide. And we do this by kind of trying to quantify the impact that erosion has on rate of input of carbon and organic matter into soil, the rate of loss through microbial decomposition, and a whole host of other physical chemical processes that change when land is eroded. And then the other major topic in our lab is fire and what happens to soil organic matter dynamics in post-fire environments, in particular when you have lateral redistribution of topsoil after fire, and what happens also to this pyrogenic matter or fire-altered organic matter that is created by combustion of biomass. So this pyrogenic organic matter is basically condensed aromatic structures that are partial combustion products from biomass burning, but they can last in soil for long periods of time and they're super reactive. And so they play major roles in improving soil physical and chemical properties, but also have implications for soil biology. And it's become a major topic in soil organic matter these days because we're learning that something like 30% of all the soil carbon globally could potentially have been fire altered or could be pyrogenic in its nature. So we've asked a lot of questions in field lab settings to understand how fires cause destabilization of topsoil and breaking up of aggregates in a process that kind of kickstarts erosion and lateral distribution of this pyrogenic carbon-rich topsoil after fires. And we've also tried to explain what are the factors that determine how fast pyrogenic carbon would be eroded after fires. In particular, we're interested in doing this because we had a hypothesis that erosion must play a major role as a factor that determines persistence of pyrogenic carbon post-fire. And it turned out we were right. And a few months ago, we released this commentary, which was more of a conclusion to a number of the papers that we've written on this topic, that in fact, the major conclusion is that the first interaction of water with pyrogenic carbon that occurs within very, very short periods after fire is really the primary factor that controls its environmental persistence. And then another kind of topic that has been a major focus in our work lately especially has been deep soil organic matter, which basically we're peering deeper to understand where exactly is carbon in soil. So a lot of the work, as much as you've heard, there's a lot of work in soil carbon lately, a big majority of that work actually only looks at the top 10, 30, maybe 50 centimeters of soils, but soils can be way deeper than that. In fact, when we explore different soils across different parts of the world, we see that sometimes, for example, the soil in this spot that I'm circling at 2015 elevation in the Sierra Nevada mountains extends 10 meters below the soil surface. And so we're trying to understand what proportion of this carbon is in deep soil? How climate sensitive is this pool of carbon in deep soil? And if so, which climate variable? Turns out it's precipitation that plays a major role. And then doing some global extrapolations to understand what proportion of carbon in soil or how much can exist in deep weathered bedrock, C and CR horizons in soil terminology, which so far have not really been part of the global accounting. And we've seen results something like the amount of carbon stored in soil could potentially be higher by 201 petagrams of carbon, about 201 billion metric tons is what we're talking about, if we actually accounted for carbon storage in weathered bedrock. And then we've taken some real long-term, I don't know if I could do this, but I tried to mute that attendee that is, it's not working for me. Okay, another thing that we've focused on is trying to use a long age gradient of soil. So soils that developed anywhere from about 100 years ago to soils that developed and that have been weathering for up to 3 million years. And bringing that perspective of the length of time that we have over this long age gradient soil then to understand how over time as soils develop, their properties, their fundamental properties change, as well as their ability to regulate biological processes, including carbon storage, but also enzyme activity, biomass production, and even the distribution of microbial life, in particular between bacteria and fungi. With that, I think I'll stop and move quickly into the topic of soils and climate change. Okay, so to start with, I want to remind you that me as a soil scientist, when I'm talking to you about climate change, fundamentally it has to do with the fact that soils store large amount of carbon. So there's about 3,000 billion metric tons of carbon that is stored in soil. And if you put that in context of the amount of carbon stored in the atmosphere and vegetation, soils store twice more carbon than all the carbon that is in the atmosphere and vegetation right now combined. So that's a lot of carbon, obviously, right? And soil, as far as carbon is concerned, kind of operates like a bank, right? At any given time, the amount of carbon stored in soil is a function of how much is coming in and how much is coming out. And carbon fundamentally, kind of basically speaking, mostly comes to soil from plants. And that's the carbon that plants take out from the atmosphere during photosynthesis. And once they use the CO2 in the atmosphere to build their biomass, then that carbon enters the soil when those plants die or when the organisms that feed on the plants die. So that's the major input variable or deposit into the soil carbon bank, if you will. But once in soil, organic matter is cycled by activity of microbes, in particular, groups of heterotrophic aerobic organisms decompose most of the organic matter at or near the soil surface. And this microbial decomposition or breakdown of organic matter is a critical process for many reasons, because first of all, it's the process by which our waste products, including waste of all living things, obviously our residue gets recycled. It's also the process by which the nutrients that the plants took up from soil when they were growing up also get liberated and become available for the next generation of living things that live in soil. And the byproduct of the process of decomposition is also CO2, in particular from aerobic decomposition is CO2. So it's a very, kind of important process, decomposition, and is kind of the main, mechanism for loss of carbon from soil into the atmosphere. So that's like the withdrawal from the soil carbon bank, if you will. Historically, the input and output terms to the soil carbon bank were roughly balanced. In fact, over long periods in the Earth's history, there was more input than output, so the soil carbon bank built up. and built up to the point where, there was the rich amount of, the soils became rich in terms of their health and the amount of carbon they stored. But obviously now we're worried about this carbon bank potentially getting, the withdrawal getting too big. And I'm going to get to that point in a minute, but I just want to mention that, so as I indicated, this large stock or reservoir of carbon in the soil means that any small change in the amount of carbon taken up from the atmosphere and stored in soil, or any small change in the rate at which carbon is being decomposed from soil and the greenhouse gases released to the atmosphere, has a huge implication for maintenance of the Earth's climate system, because both of these processes are affecting the concentration of greenhouse gases, right? Either by taking up CO2 during photosynthesis or releasing CO2 and other greenhouse gases during decomposition. And the other thing that I want to mention is also that soil is a big carbon bank, as we've discussed, but this also has another thing that makes it super important from the perspective of climate, and that once carbon enters the soil, it cycles very slowly. Once carbon comes into soil, as I mentioned, a lot of it decomposes rather quickly and is released into the atmosphere as greenhouse gases. You can think about that pool of carbon more like a checking account. We all feel rich when our paychecks hit the account in the beginning of a month. Our account balance is huge, right? But very soon, in a few days, we have to pay the bills, we have to pay rent, we have to pay the car payment and the insurance and all of that, all the things that we need to make our life possible, right? And so that balance looks a little smaller, obviously, after we do that. So this pool of carbon that quickly cycles and is important for provision of nutrients to soil is more like a checking account. But soil is also able to stash a little bit of the input of carbon every year, if you will, every season, and store it in pools that cycle very slowly. And these to me are more akin to our savings account. And this carbon saving account in soil is made possible by the fact that soil, in addition to organic matter, also has reactive minerals. And these reactive minerals are actually very, very effective in storing, not just storing, but also stabilizing carbon, meaning carbon, when it exists, even in particulate form that could have decomposed quickly by microbes, if it exists in physical association with these reactive minerals inside aggregates, as we call them, or clods in soil science, then it could persist for long periods of time, because once carbon is inside this physical association entrapped by these aggregates, microbes cannot effectively degrade it. And the reason is because these aggregates, especially small size aggregates, are so small that microbes cannot physically enter them. And even things like extracellular enzymes that are needed to break down the residue cannot penetrate these aggregate spaces. Water cannot also penetrate effectively into these deep aggregate spaces. So as a result, once carbon is inside these aggregate spaces, it's physically hidden or physically protected and stabilized against decomposition. So it lasts there for long periods of time, hundreds of years sometimes. And then there's even another mechanism where reduced organic compounds, where most organic carbon is in soil, these compounds can form chemical association with reactive minerals. So now what we're talking about is organic compounds actually forming chemical bonds with the surfaces of reactive minerals. And that is actually an even stronger association that stabilizes carbon even for longer periods of time, because microbes, if they want to degrade this organic matter, they have to break the bonds between the organic compounds and the reactive minerals. And that takes energetically, that's an expensive process. So if they have other sources of carbon, they'll just leave that alone. So a small amount of carbon that's stashed in this physical or chemical associations with minerals then is able to last and build, first of all, the savings account for carbon, but then it also allows carbon that would have decomposed in a year or two if it was at or near the soil surface to stay in soil for hundreds and thousands of years. So soil is not just important for storing a lot of carbon, but also it stabilizes a lot of carbon in slower cycling pool for long periods of time. With that, I hope I've convinced you the importance of soil. But I have to say that as important as these processes are, right now we're facing some major threat to the ability of soil to actually continue to provide the service of carbon storage and stabilization. And that's because the way we've been using land, in particular in agricultural systems, conventional agricultural systems, and the way we've been altering the landscape overall with things like deforestation, has now meant that about a third of all the soils globally are degraded. About a third of those soils globally are losing some of their productive capacity or capacity to support plant production. And if soils can't support plant production, first of all, the input of carbon to soil is reduced. But then these practices are also causing rather rapid decomposition of the carbon that was in the soil. So both of these mechanisms, both of the two fluxes, like the input and output terms for the soil carbon bank, are going in the direction we don't want them to go because of human use and abuse of soil. And this, as you can see in this map, the type of degradation varies globally. The extent and severity of degradation also varies globally. But you could see rather clearly that it's all over the place. All over the place, soils are getting degraded. And the carbon cost of all of this degradation is immense. And the bottom map now shows you the soil carbon change that is starting from 1971 and what we're expecting to go all the way to the end of this century, the 2100, that is occurring as a result of land degradation. And in fact, by some studies, we've seen that human use and abuse, in particular in agricultural areas, in the last 200 years or so, has caused the loss of 120 petagrams of carbon from soil to the atmosphere. 120 billion metric tons of carbon that was in the soil carbon bank has now been lost to the atmosphere because of how we've been using soil. That's the opposite direction of what we wanted to do, right? Even worse, we right now have to deal with the consequences of warming in the circumpolar north or Arctic systems that is causing large-scale thawing and draining of permafrost soils. Permafrost soils are soils that have this permanently frozen layer of ice underneath them. And these soils store, northern soils, higher latitude soils, store about a third of all of the world's global soil carbon stock, and have been super effective in accumulating carbon, partly because these soils are able to, to support plant production during the short growing season that they have in their summer months. But because the environment rather quickly turns to be cold and really dark for much of the year afterwards, the microbes in this environment cannot effectively break down the residue. So as a result, there's been a lot of input to the soil carbon bank, but rather very little withdrawal over long periods of time, hundreds of thousands and millions of years on these systems. But now, with the rather rapid warming that these areas are seeing, we're seeing widespread thawing and draining of permafrost. And what thawing and draining of permafrost do is it removes the physical barrier that microbes had from decomposing organic matter. So now there's nothing stopping them, these microbes, from rather quickly decomposing the carbon in these permafrost soils. And they're able to really degrade it extensively, with the potential of releasing hundreds more petagrams of carbon into the atmosphere from the permafrost soils to the atmosphere in the form of both CO2 and even the more potent greenhouse gas, methane, depending on the hydrology of the system. But that doesn't even stop there. That's not even the end of the story, right? So more and more of this carbon dioxide and methane that's released to the atmosphere also goes into fueling an even warmer climate and causing even further global warming, which means that further global warming causes further thawing and draining and further degradation. And it's kickstarting basically a positive feedback loop that keeps reinforcing itself over and over and over again. And there's so much carbon in the soils that it's feared that it could really change our climate future if this keeps happening the way it's happening right now, or the way we fear it will unfold over the coming decades. Okay. But it's not all bad story, right? Because I want us to put into, as we start talking about mitigation strategies, I want to first put in context what we've learned and where we're heading. So this is a figure that came from a paper, a fairly recent paper that came out that basically plots the atmospheric concentration of CO2 given in parts per million in the last 100 million years of Earth's history. So you see the different colors here matching with the different geologic eras and their past climates here on the top. So what we've seen basically is that throughout Earth's history, we've seen fluctuation of atmospheric concentration of CO2. We are right here near the top of this darker blue line here. When it starts getting lighter is when it's modeling, that's filling in the gap. So we've seen some fluctuations, and if we continue on the slope that we're in right now, there are many different possibilities for where we're heading. So first of all, if we continue on business as usual, factoring human population increase and our consumption patterns, then there's not a pretty good chance that we can end up at a pretty high emission scenario, which would be unlike anything the Earth has seen in the last 100 million years or so, right? But then we can actually work towards reducing emissions, which is one of the first things we all have to agree we need to do, right? We can reduce emissions of fossil fuel and avoid this rather disastrous high emission scenario that we could be at if we follow business as usual, and arrive at a middle of the road scenario when it comes to concentration of greenhouse gases in the atmosphere. And that would obviously allow us to avoid some of the more extreme impacts of this high concentration of CO2, but it's still really high. It's still this middle of the road scenario that we could get to by just reducing emissions is still unlike anything the world has seen in the last 20, 30 million years, right? But if we could actually couple reducing emissions plus sustainable practices that would take out CO2 from the atmosphere and put it in soil, and which we collectively refer to as climate smart ecosystem management practices, then not only do we have a chance of avoiding both of these disastrous scenarios, but we even have a real potential of bending the climate curve. And in fact, pretty much most people who do this work right now agree that if we want to limit atmospheric warming to something like 1.5 degrees C or so, we have to both reduce emissions and figure out ways for negative emissions, figure out ways where we can take down CO2 from the atmosphere and put it in slower cycling pools in natural ecosystems. And soil is an important part of those natural climate change solutions. Over the last many years that people have been doing this work and crunching these numbers, we figured out many options that we have for climate smart land management. These are all options that we know are effective for taking out CO2 from the atmosphere and storing it in soil in process that we recognize as carbon sequestration. And there are many different variety of processes because not every practice is suitable for any given area, but rather depending on the environmental conditions that we're working with, depending on the type of soil, that we can implement an appropriate climate smart management practice. So let me kind of help you with this figure. So what you have on the x-axis is the potential for greenhouse gas reduction or removal from the atmosphere, given in megagrams CO2 equivalent per hectare per year. It's given in CO2 equivalent because it's accounting for not just CO2, but also methane and nitrous oxide. So it's more of a greenhouse gas mitigation strategy, not just a CO2 mitigation strategy is what we're talking about. So this is the potential per given unit area over time. And then on the y-axis, what you have is the potential land area where we can implement these practices, practically speaking, right? So the most kind of effective greenhouse gas removal strategy that we know of is restoring histosols. And histosols are these organic soils that exist in wetlands, mangroves, and coastal type of environments. And they're in many ways very similar to the permafrost soils that I just talked about earlier in the northern higher latitude environments, but there's no permanently frozen layer underneath histosols. They're just soils of wet environments. So when the plants photosynthesize, the residue still accumulates because it's too wet for those heterotrophic aerobic microorganisms to effectively break it down. So not the cold climate here, but rather it's the moisture that limits the degradation of the residue. But so we know that this is really effective in terms of a removal rate of greenhouse gases from the atmosphere, but we also recognize that there's a geographic limit for where we find these types of environments, right? With wetlands, for example, or mangroves. The climate envelope where these ecosystems exist is rather narrow. So the area of practice or adoption is small, but still, because of the high rate, it could still add up to 1.3 petagrams of CO2 equivalent that could be removed from the atmosphere per year globally. And then on the other extreme, you have a whole host of different practices, for example, that do not have as high greenhouse gas removal potential per given land area or year, right? But by the virtue of these being able to be deployed across large areas globally, we can still achieve either at least equivalent, if not more, overall carbon sequestration as the restoring histosols. And this includes things like managing our grazing lands better, in particular, avoiding overgrazing, restoring grazing lands by using things like compost, for example, that increase plant productivity, and even addressing cropland management practices, which mean avoiding over tillage, adoption of conservation tillage practices, avoiding using of excessive agricultural chemicals, and even adding things like compost when they are available and biochar. And of course, if we can adopt deep-rooted perennials as opposed to shallow-rooted annuals, we can also achieve very similar sequestration rates. And in fact, there's this effort that started in France called the 4 per mil effort that has been trying to get a wide-scale adoption of climate-smart land management practices. And according to their calculations, if we can aspire to increase the amount of carbon stored in soil by 0.4% annually. So all we're talking about is 0.4%, right? So 4 per mil annually. That could be enough to remove 1/3 of all the global emissions of CO2 from the atmosphere. That's about 3 gigatons of carbon that we could remove from the atmosphere if we could effectively deploy these climate-smart land management practices. And I don't want to go too much into detail here, but others have also done work to demonstrate that not only are these practices effective in removing carbon dioxide from the atmosphere, but they also are cheap relative to all the other solutions that we have for carbon removal from the atmosphere. And they come with multiple benefits for improving air quality, maintaining biodiversity, improving access to clean water, as well as improving overall soil health. Others go a step further even in linking these practices with improving human condition globally to demonstrate that improving soil health, where soil carbon sequestration is at the center of improving soil health, is key not just for climate change mitigation, but also for ensuring food and nutritional security of people around the world. Keep in mind, the reason why organizations like the UN are involved in these kinds of efforts and why scientists are drawing the parallels with between soil carbon sequestration and the sustainability goals of the UN is because healthy soil is key for the survival of people around the world. And as the world's population keeps growing, the demand for soil to produce the resources we need keeps increasing. Close to 1 billion with a B people around the world right now lack sufficient food and nutrition for their livelihood. And a lot of this has to do with degradation of soil. So improving soil health is at the center of this. So, and part of the reason why I think you have to think about it in this way is that in the context of food and nutritional security globally, climate change is a threat multiplier, meaning human-caused climate change is now exacerbating the already existing threat of food and nutritional insecurity, for many reasons, through droughts, through unpredictable weather phenomena, through causing land degradation, reducing yield of crops, increasing food prices, and many other issues. So what I'm telling you is that climate change and food insecurity are connected in many ways, and they're both underlain by soil, and improving soil health is key for addressing both of these major threats of our time. Okay, that leads me to the last part of my talk. I'll try to make it quick. And I want us to kind of speak together about why me as a soil scientist who studies climate change also thinks adoption of principles of justice, equity, diversity, and inclusion is important. First of all, I hope that last slide showed you that soil science is important for everybody's welfare, right? It's critical for food and nutritional security, but as we've shown in that science paper that I mentioned before, it's also even critical for national security. And we're right now at a point where there is an urgent need to center soil science and center soil science in our climate discussions in a way that allows us to think about not just climate change, but also how it's related to things like land degradation, loss of biodiversity, and other issues. And remembering the fact that most of the people that are experiencing the brunt of climate change, land degradation, and loss of biodiversity and their impacts are Black and Brown people, which lack the economic means to be in the academy, and they had been, in many ways excluded from the academy. I think it's high time that we actually openly speak about what the cost of that exclusion has been, and recognize that our community in particular, soil science, geosciences, earth and environmental science in general, are some of the least diverse fields, even with STEM. And that has implications, right? And it has implications because it means the voices of the people that are most affected by these really global phenomena are missing from the conversation in many cases. And as I go on talking about diversity and inclusion, I want to make sure that we're pursuing the moral case for diversity here. I don't want us to talk about diversity because diverse teams produce highly cited papers or it's good for the bottom line of companies or things like that. I personally believe that we should only be making the moral case for diversity. Everybody deserves fair, access to education and the careers that we all enjoy, but everybody's voice also needs to be heard. And one of the only ways I know how to do this is to shine a bright light on the demographics of our academic community that doesn't really represent society at any level at this point. And as you look at this graph, I want you also to remember that the demographics of a group and an institution provide a window into the culture, climate, equity, and inclusion of scholars from minoritized communities. And I also want you to remember that none of the data that I showed you should be a surprise. And it's even been that way for many decades at this point, even after, as we keep talking about diversity a lot over the last 4 or 5 decades, the numbers have barely changed. More than 80% of the PhDs in the broad field of geosciences, and that includes all of these fields that I've listed at the bottom here, more than 80% still go to only white people. I picked 2018, which is one of the years that has complete data sets already, that in 2018, only 11 Black people received PhDs in the geoscience across the entire country of the US, the entire country. And then it's even worse when you look at numbers like American Indian and Alaska Native. That number was 3 for the entire year across the entire country. A little better for Hispanic or Latinx folks, but still not good compared to their representation in the population. So we have a major issues with the diversity, right? And this, obviously has implications. And I want to emphasize that we can look at these numbers and ask ourselves, how did we get here, right? why is this the case in our field? A lot of times we talk about this in our academic communities as a leaky pipeline issue. We say there's lack of diversity because people from minoritized communities keep dropping out of this pipeline, drip, 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 right out of the leaky pipeline. And I feel like our academic community is getting a little too comfortable with this notion of a pipeline. We keep hearing that there just aren't enough people pursuing majors in our field. That's partly true, but that's not the whole story. But I would argue that the idea of a leaky pipeline is not only incomplete, but also pervasive and damaging story we keep telling ourselves. And we even use it to indicate that scholars of color, in particular Black people in STEM, are rare creatures, as the president of Purdue University likes to say. But I find a lot of problems with these metaphor and approaches, to be honest with you, because it hides the fact that people are not just passively dripping out of this pipeline. It hides the fact that they're actually being pushed out. And it also really cannot help out to address this issue, because presumably if this is a leaky pipeline issue, if we just ram enough people through the pipe and push a lot of early career people, then the problem would resolve itself. But that's really hasn't happened in the last 4 decades or so, right? So my argument is that we need to get real and acknowledge that most of us work and study institutions whose structures, practices, and behaviors were precisely designed to serve only one segment of the population, the kind of people that you see in the left here, right? These are the folks we hail as leaders, fathers of our field, whose stories, explorations, and discoveries we fill the pages of our scholarly works with, right? These are the kind of people who had historically thrived in the scholarly community, the only people really who had a chance to pursue the kind of science that we all love and set the narrative for our scientific community. The system that enabled the success of these people, though, continues to exclude the rest of the human population. I would argue that the system that we have right now is better represented as a vicious obstacle course that people from minoritized communities have to overcome to succeed in our field and be members of this scholarly community. And that vicious obstacle course, I think many people would agree with me, is marked by continuous lack of support, many obstacles that people of color face in the academy, bias, harassment, and discrimination. Again, I won't stop in here, but I just want to highlight that this lack of equity in the system is represented at every step of the academic process, starting from when people start graduate education in particular, and even undergraduate research and mentoring they receive, all the way to retention in the career and even who gets recognition later on in their careers. And I feel like until about last year, when the protests erupted all over the place, we had been very hesitant to talk about diversity in the academy. But that's quite a problem, obviously, because for many, many Black people in particular and people of color, the entering academic institutions had been both a dream and a nightmare, where it's been an exhausting and corrosive experience, and many drop out because of harassment and discrimination that occurs in our workplaces. In fact, some rampant harassment of all sorts and discrimination had been documented in our professional societies, and academic institutions in general are only second to the army in terms of the prevalence of harassment in the workplace. That is quite a story to tell, as you can imagine, and it's really troubling, but it doesn't even stop there. Many, many people tell us when we ask them, have you experienced hostile workplaces? And has that made you consider leaving the geoscience? Many say yes, in particular, Black women, non-binary respondents, and folks from across multiple minoritized communities. So the bottom line of the story for me is we need to figure out a way to treat people better than we treat data in our academic institutions. You and I and every student that we teach knows very well the consequences of plagiarism, mistreating data, right? And nobody would dare cook data or fabricate data because we know it's wrong. And we also know that the consequences of engaging in that kind of practice. But we don't really have strong practices like that for actually mistreating people. So to me, I think it's really important, and this comes out of the work that we do with a fabulous group of folks in the Advanced Geo Partnership. We are really interested in figuring out ways that we can help our academic community treat people better than data. As one of our contributions in this field, a colleague, Bala Chowdhury, and I last year wrote a paper that was pretty well received in the scientific community of 10 simple rules for building anti-racist lab, which is basically what we think we all could do to address these issues in the academy. And I'll kind of leave this one up here as we have a discussion, and I thank you all for your attention. Took me a couple of minutes longer to account for that hiccup. I apologize for that. Thank you.
That was wonderful. No worries for time, because I believe everyone enjoyed it. And thanks for so insightful talk. Please allow me to give her a round of applause.
Thank you.
So you can enter your questions in the chat box. So feel free to enter your questions in the chat. Yeah, students in my class, you will be counted. So please enter your questions. Yeah, maybe I can start here. So I guess the first question I had is like, of course, I feel like where you going in terms of like addressing race and racism. But I guess my first question is like, how did you start working in this direction? Because often people like me working and trained in soil science or like physical sciences domain often don't get the training that is needed. So if you can elaborate a little bit on that direction.
Sure. Two reasons. One is, I think after I finished my undergraduate degree in soil science and started learning about erosion and land gradation, I felt like I didn't have the right basis to think about the societal context of these issues. So that was the motivation for why I pursued a master's in political ecology. And I find that to be tremendously useful. Second, my own experience in graduate school shaped this. For better or worse, the experiences that I had in graduate school, which were not great, just to be clear, in particular of how, individuals can make people's lives hell because, not having, in my case, I was told to my face that I didn't have the right pedigree to be able to do this kind of work in biogeochemistry or enter the elite institution that I was doing my PhD in. And that was quite shocking. It took me a long time to accept that that's a thing that people even say and do to one another. But once I was able to find supportive mentors to help me work through the difficult path, I think it was kind of inescapable after that for better or worse, this was part of my path and part of my history. And I was determined when I got my own lab in my own position that if I have any say in it in my own institution, students were not going to experience what I experienced. Kind of why also I work in the graduate division right now.
Thank you.
I mean, it's not a great story. It's not a happy story, but that's what it is.
Thanks for sharing.
Yeah.
I think we have a lot of questions in chat now. So can you speak a bit about the impact of urbanization on the ecosystem services provided by soils and the capacity for the use of soils, specifically in the urban environments, to drive climate change mitigation?
Yeah, that's a really good question. And I have to start by saying that a lot of soil scientists, ecologists, biogeochemists do not typically study urban environments. And that's reflective in how much we understand so much about undisturbed ecosystems, but not as much as the ecology and the kind of biogeochemistry of urban ecosystems. But the last couple of decades, in particular, the last decade had seen quite a lot of activity on urban biogeochemistry and ecology work. And what we're seeing is that obviously, urbanization changed the ecosystem in major ways, right? This built environments and sealing of surfaces and restricting, kind of redirecting hydrologic flow paths and heat island effect. All of these things are major variables on how ecosystems are altered by humans in urban settings. When it comes to biogeochemistry and carbon sequestration, though, we are coming to appreciate that there is a lot more carbon stored in urban soils than we thought. And part of that is because if you think about how we maintain our urban gardens and urban lawns and things like that, and parks, right? Even though there's a lot of inputs that go into that system in the form of irrigation, water, and nutrients, all of that translates to soils that actually have a good amount of carbon. So I can't give you a number that is accurate about how much carbon is stored in urban soils, but it seems a lot higher than we initially assumed. And so there's a number of active efforts to try and get a better quantification of that. And that's, I think, an area of growing interest for a lot of people.
Thank you. So Atlanta is in the middle of a spring pollen storm. So how does this impact soils and microbial population can have in this season?
That's interesting. That's not really how I think about soils usually, but I would assume, I would assume the pollen is, kind of, I wonder if the person that asked this question is thinking about it in the perspective of spreading plants, kind of type of plants all over the place and allergies, or I assume it's going to spur activity by microbes because it's a fresh source of nutrients, right? But I can't really tell you exactly beyond that what it would do in this context, in particular in a city like Atlanta. I don't know, Jenny, maybe you have a better insight in this than me.
I'm just starting learning about Atlanta.
Yeah. Yeah.
David, if you want to speak up, I know you asked this question. You're more than welcome to do.
Yes, it just seems like it's a remarkable source of nutrients in food.
Yeah.
And it is so abundant, largely because of the number of angiosperms that have been planted in the urban area. So is that constructive, is that helpful, or?
I'm sure. If you're just thinking about it from the perspective of microbial activity and abundance, as long as other resources are not limiting microbial growth, then yeah, that could only be a positive thing.
It also fills the waterways, all the streams and creeks.
That's probably not helpful from a water quality perspective.
Right.
Yeah. Yeah. Thank you. I appreciate the explanation. I wasn't sure.
Okay, the next question is, what impact has the accelerated growth in American Midwest of corn for the production of ethanol have possibly had on soil and our environment?
Yeah, so anybody who studies agronomy and soil science would tell you that corn is one of the most terrible things we could do to soil, partly because of the way that corn has to grow. It just ends up becoming a major variable in soil degradation and in particular the increasing rate of erosion, as you have to till the land every year and then plant a row crop like corn that doesn't provide sufficient protection for soil. The biofuel studies, the biofuel angle is an interest one because corn's obviously problematic. I think everybody would agree. But there are now discussions around things like switchgrass, deep-rooted perennial grasses that are also biofuel crops. So those, though, are discussed as being potentially helpful for carbon sequestration, not just as biofuel crops when they're in terms of their above ground foliage, but that the extensive rooting system that plants such as switchgrass and other biofuel crops that are perennial, deep-rooted perennials, how they contribute to carbon storage and stabilization in soil. In fact, we have a couple of ongoing projects to look into switchgrass and similar deep-rooted plants to look into the implication of those for carbon sequestration right now.
So what are the most promising policies for cities to address these carbon issues? Can you list a few?
Yeah, I mean, again, perennial grasses and trees stand out as being particularly effective strategies for cities. Partly because both of these are, long-lived plants that continue to take out CO2 from the atmosphere and pump it into the soil. And they also are good for lowering the heat island effect in urban environments. So all in all, a win-win in reducing pollution.
Well, our next question is, do you have any research experience with carbon sequestration in low oxygen soils? I was talking with a scientist friend of mine, and he mentioned climate solution like these where we bury dead or dying trees under the ground in low oxygen soil so that they decompose much more slowly. So you mentioned about histosol already.
Yeah, so that's essentially what histosols do, right? It's under wet conditions. So in soils, you have pore spaces in between the mineral organic particles, and those pore spaces are where water and oxygen go. And so if the soils remain wet, it means they have low oxygen. And under those conditions, the organisms, the microbes that are most effective for breaking down residue are not effective. So the aerobic heterotrophic organisms that are most effective in breaking down residue. So organic matter that finds itself in any situation where there's low oxygen, or i.e. waterlogged or saturated landscapes, tends to remain there for long periods of time. So that's kind of the main part of the story. But keep in mind that under certain conditions, residue decomposition under anaerobic or low oxygen anoxic conditions could also lead to release of nitrous oxide and especially methane from soil. And those could be problematic. So whenever people are talking about burying organic residue under low oxygen conditions, it's really important to keep in mind that what we don't want to do is increase methane fluxes at the expense of reducing CO2. Both are harmful greenhouse gases. So whenever people are discussing histosols or burying residue under low oxygen conditions, we have to, do our calculations and studies to make sure that it's not going to increase methane fluxes.
Thank you. I think the next question is, so Connor is asking, and I have to scroll it up now. Give me a minute.
I think I see this one about the number 7 suggestion.
Yep.
And then number 8 to adopt a dynamic research agenda. Thanks, Con, first of all, for talking about this with your colleagues. I really appreciate this. That's the first thing we all have to do. But let me explain to you how I think about this. First of all, the thing we have to expect to realize is that a lot of students from minoritized backgrounds, they could very well be super interested in the science, but they also are interested in societal implications. So when we say adopt a dynamic research agenda as you intentionally recruit BIPOC students and staff, we're not saying change your research agenda completely. That's not the point here, right? If students are coming to work with you, they're coming to work with you because they're interested in your research area. But if they are interested in, say, looking at the societal implications of what you're doing, and that's not really your forte, that's not your expertise, how about partnering with social scientists or humanities folks or artists in terms of communication on the topics that you're working on? right? So the issue is not that you have to radically transform your lab's research agenda to welcome people into the group. Rather, it's to be slightly flexible in terms of how you execute your research agenda so that you're open to people's ideas, suggestions. And I think this is particularly true going forward. A lot of the next generation early career researchers are way more interested in societal implications, policy implications of the work that they do, science communication and things like that, way more than people, a generation or so before them. So if we're really going to recruit the best and the brightest in the coming generations, regardless of whatever race they're coming from, but this happens to be always true of students from minoritized communities, then we have to all be willing to be flexible in what we allow students to do and early career researchers to do in our labs. I hope that clarified the point.
Thanks, Dr. Berhe. So we have a few more questions. Is it okay if we can go one by one?
I'm okay, yeah.
Okay, thank you so much. I guess the next question is really interesting. How does ocean acidification can affect sandy soils?
I'm a little confused about how they're relating ocean acidification and sandy soils, because by definition, ocean acidification is happening away from what we technically call soils.
I guess the question here is to look at like dunes near the beaches. Like if ocean
the major issues with things like ocean acidification, right, is bleaching of coral reefs and kind of altering of the rates of biogeochemical cycles and selection for different groups of microbes. And I guess if you think about it that way, then the dunes nearby will also get affected, if that's what you mean. Yeah.
So is there potential to genetically modify plants to improve their capacity to sequester carbon?
Yeah, it's in fact, a lot of what I discussed with the deep-rooted perennial discussions right now are in the area of genetic modification of plants. But genetic modification of plants with the purpose of making sure that the annual crops that we use in agricultural systems get more extensive rooting systems so that they are contributing a lot more to carbon sequestration in soil than the shallow-rooted annuals typically do. There was a question that I really liked right before that one about genetically modified. It's okay, I'm happy to address that. Sam asked, how can indigenous and local knowledge help inform land-based mitigation in reference to climate-smart land management practices? Thank you for asking that question. I like to remind folks that a lot of what we know in soil science is really based on a lot of indigenous knowledge, right? The people that we call father of soil science and this and that, all, in many cases, what they did is they formalized what communities around the world knew about the soil in terms of how to manage. And communities around the world, indigenous communities, then they had learned over generations about how to best manage their land, how to make sure that their land remains healthy, and that their management practices are sustainable. And so a lot of what I just mentioned as being climate smart land management practices are actually things that small-scale farmers and indigenous communities all over really practiced. They were the management practices in many cases that sustained the land and maintained its health over generations to support human life and civilization. The problem arose when we, came out with the plow and our, synthetic fertilizers and everything else to make agriculture more intensive, and that caused a rather rapid degradation of soil that is now becoming a problem. Other than that, I think historic communities manage their soil well, and there's so many stories out there about communities and civilizations that thrived or collapsed based on how they manage their soils. And there's tons we can learn from local indigenous knowledge of the communities that actually managed to sustain their soils and their health of their soils over time.
So Molly asked that I have been waging war against wisteria in my yard because it is invasive and attacks trees. However, I'm more and more impressed with its ability to accumulate carbon in its massive biomass. So I have begun to think, is there any way that it can or could be useful in banking carbon?
That's an interesting point. I mean, a lot of invasive species grow really fast, right? And so they store a lot of carbon and biomass. But I guess I would put this in context of the health of the overall ecosystem. And maybe, depending on how it's affecting the health of the overall ecosystem, one benefit could be to just bury the biomass, make sure it's not harvested or removed so that it actually contributes to buildup of carbon in the soil. Yeah, that's an interesting question.
So are the carbon stabilization mechanisms in aggregates and chemical association the same in histosols? Or does the slow decomposition of organic matter mean that doesn't happen in the same way?
Now, they're a little different because in histosols, it's still a physical stabilization of carbon, but it's that physical stabilization that's made possible by the microclimate or environmental conditions in which the residue finds itself in, right? In histosols, in situations where you have histosols and wetlands, the soil is too wet to allow growth and activity of aerobic heterotrophs that I mentioned, the bacteria in particular and the fungi that are important for degrading residue. So as a result, the residue accumulates and builds up as soil carbon. But what I discussed in the context of aggregates and the chemical bonds that organic matter forms with mineral surfaces, those are more things that are happening with mineral soils. So in soil science, we make a distinction between mineral soils and organic soils. Organic soils are things like soils that you find in histosols, where at least 20% is organic matter by mass. So what that means is there may or may not be a lot of minerals in the mix actually when you have histosols. But some histosols have a lot of sand, and then sand plus the residue organic matter. But the physical and chemical associations that I discussed, they're more common in what we call mineral soils, soils that by definition have less than 20% carbon, or 20% organic matter, which is equivalent to about 12% carbon, which means most of the soil is actually made out of minerals, clay, salt, silt, and sand particles. So the mechanisms are actually different. One is climate that's restricting the rate of decomposition. The other is where the residue or carbon finds itself in the context of minerals in the soil.
Thank you. I think our last question of the day is, compared to other STEM fields, what do you think makes the environmental science field in particular flexible in terms of feeling more like a humanities field opposed to a more stereotypical STEM field such as engineering, biology, chemistry, etc.?
If I understand this question right, I think part of it is we're dealing with real life things that affect human lives, right? More directly than say, abstract concepts in chemistry or something. That would take, 2-3 steps before we can see the human implications. I wonder if that's what you mean. So there's a direct impact of our field in our work that we could see in terms of how it affects society. Is that what you mean? I'm trying to wrap my head around the question.
Yeah, this is
sorry,
the last.
This is the last question. Yeah, I assume that's what they meant. Yeah, okay, great.
That's
Yeah, so yeah, I think we're good. Thank you for clarification. Indeed, you're right. This is a field where there is we see the direct impact of the things we're studying on human societies. And we're also trained to see interconnections, right? And connections between the different spheres and how humans fit in this natural ecosystem, and how humans, though small compared to the Earth system, have had, long and really, really remarkable, in a not a great way, influence on the natural ecosystem, right? So by being trained to see these connections and direct impact of the work that we do, I think I could see with you that maybe that's where the humanities feeling kind of comes in. Thank you.
Thank you so much, Dr. Berhe, for staying with us more than like 13
No worries. Thank you all. I appreciate it.
Yeah, please give her another round of applause. We are really grateful to hear from you about the perspective of soil climate and racism in this environment.
Thank you so much.
Yeah, thanks for attending. everyone.
Appreciate it. Thank you, everyone. Thanks all. Bye.
Thank you so much.
Bye.